Welcome to this lecture in mechanical operations. In the last class we started discussing a second method of mechanical separation, which is filtration, and looked at various types of filters and so on, particularly the differences between fibrous filters and membrane filters. And then towards the end of the lecture I started discussing standards for testing and certifying filters, and I mentioned that there is this organization called ASHRAE which has responsibility for setting these standards worldwide. So how do you certify a filter? You have to take the filter medium and challenge it with contaminants, particles. You measure the upstream concentration and the downstream concentration, take the ratio, and that gives you a measure of filtration effectiveness, right? But the challenge of course is, what do you challenge the filter with? Because filtration efficiency, as we have seen before, will very much depend on the physical characteristics of the particle, size and shape primarily. Even if you exclude chemical effects and just concentrate on physical separation, shape and size have a significant effect. So you cannot really certify a filter across all sizes. The certification depends on how the filter is challenged. So there are some standard techniques that have been developed for challenging filters also. There is something called dust holding capacity. Dust holding capacity is a reflection of how well a filter can separate common road dust. And here again there are standard road dusts. There is something called the Arizona road dust, which has been adopted as a worldwide standard. It has a certain composition, it has a certain size distribution. So you can challenge the filter with this road dust, and what you will get then is a measure of its dust holding capacity. There is another test called weight arrestance. The difference between dust holding capacity and weight resistance is in the challenge material. In the case of dust holding capacity, you use road dust. In the case of weight arrestance, you actually use a mix of about 72% road dust, 23% carbon black, and 5% cotton lint. So it's kind of a mixture of substances that are supposed to represent a wider variety of materials that need to be filtered. There is also something called an atmospheric aerosol test. The atmospheric aerosol test consists of collecting typical aerosols that are present in the atmosphere and then challenging your filter with that. Obviously this is of particular relevance for filtration apparatus to protect you from airborne contaminants and so on. So as a protective device. The fourth type of challenge is using dioctyl phthalate. DOP in liquid form can be evaporated and then recondensed under conditions where it forms nuclei of a very specific size, typically 0.3 microns. These 0.3 micron sized DOP droplets are then used to challenge a filter and assess its efficiency. Now why is this size of particular relevance? By the way, the other size range in which DOP is prepared is 0.17 microns. So these 0.17 microns, 0.3 microns have a particular relevance, and it has to do with the fact that the filtration efficiency as a function of particle size is not a monotonic behavior. As we saw in the last class, the filtration mechanisms change as you go from very fine sizes to larger sizes. It goes from diffusion to diffusion plus electrostatics to plus interception, impingement, and finally impaction and sedimentation. So if you plot this fiber efficiency single fiber efficiency that we talked about in the last class as a function of particle size, and let us say you start with 0.001 microns, 0.01 0.1, 1, 10 and so on, what do you think this curve will look like? I will give you a couple of choices, is it going to go like this? Is it going to go like this? Is it going to go like this? Or is it going to go like this? So let us say this is 1, 2, 3, 4. How many think it will look like 1? 2, 3, 4. Okay, let us do this again. How many for 1? Show of hands. How many care? 2, 1, 3, 2, 3, 3 and 4, and the rest have absolutely no opinion of any kind. That is wonderful. Okay, the correct answer is 4. Filtration efficiency has a minimum actually in a size range of roughly 0.07 to 0.3 microns. Of course, the reason for that is for particles that are finer, diffusion rates are very high and they can be captured quite easily using diffusion as a mechanism, and for particles that are larger, all these other mechanisms for large particles kick in like interception and impaction and so on. So the most difficult size range to filter is 0.07 to 0.3 microns, and in fact this is called the MPPS, which stands for maximum penetrating particle size. So clearly if you want to challenge a filter and challenge it under worst case conditions, you should prepare an aerosol that consists of particles in this size range and challenge the filter. And that is the reason why DOP, dioctyl phthalate, is prepared either as 0.3 micron or 0.17 micron droplets or nuclei, and then this is used to challenge the filter. When do you use this? I mean, clearly you need to do this only when you are trying to achieve extremely high purity conditions. Otherwise, the other 3 tests I mentioned earlier will do perfectly fine. So for example, if you need ultra pure water, or if you need an ultra pure clean room type of environment, then the filters that you use should be challenged with these very, very fine particles and well, particles in this maximum penetrating size range and tested. So for example, if you have a room that you are trying to keep clean, suppose this is a room and you want to filter the air coming in so that this room is extremely pure, obviously you have to use filters, right, to do that. So typically the way this is designed is there is the incoming air goes through filters. So there is like a bed of filters at this in the ceiling, and the air goes through these filters and enters the room, typically in a vertical flow. This type of clean room is called a vertical laminar flow clean room, and all the air before it gets in, so this room is sealed everywhere except in the ceiling through which you draw air. So you can make sure that there is no leakage and all the air that comes in is purified to a specified level. But then obviously you have to provide exhaust path, right, otherwise this, if this is a solid floor, this air will just keep recirculating. Inside this room you are doing something, you are running a process, you are making a product, you are running tools, equipment, people are inside, so there is constantly particles being generated. So if you did not have a return path or an exhaust path, even though the air coming in may be very pure, very soon the particle level will start building up inside the environment and it will become extremely dirty. So typically what is done is the clean room will have a false floor, and the false floor will have basically vents that the air can be drawn through. So all this air, instead of recirculating, will get sucked right through here and will exhaust from the room. So, this is called a raised floor clean room. The concept is that you do not want to set up recirculating paths near the floor, which will eventually cycle particles back again into the room, but you provide an exhaust path, and so you constantly keep supplying clean air and you constantly keep drawing out the dirty air. So, in principle you should be able to keep the room extremely clean with this type of a setup. Of course, you might want to consider pre-filtering this air. If you remember, we discussed last time that you need a pre-filter and then a final filter in order to achieve very high purity. So, especially for the recirculated air, you may need a pre-filter, and even for the air that is coming in, you may need a pre-filter before it goes through the final filter before it enters the room. The fresh air that comes in is called the breather air, and the air that is recirculated is called recirculated air. And in order to maintain a high cleanliness of a facility like this, you have to make sure that both the fresh air that is coming in as well as the recirculated air get filtered before they re-enter the room. And this concept, by the way, applies to product also. If you look at a hard drive, the drive itself is a mini clean room, and because the head is flying a few nanometers above the disk, you have to make sure that the interior of this disk drive is kept extremely clean. And the way they do that is essentially operating it like a clean room. There are two filters. There is something called a breather filter that filters the air coming in from outside, and there is what is called a recirculation filter inside the disk drive, which filters out any contaminants that are generated during the operation of the drive, and that is how you keep the disk drive alive and prevent it from getting killed due to particles that get caught between the head and the disk. Now, there are ratings of filters that are used based upon this challenge. There is something called a HEPA filter and something called the ULPA filter. The HEPA stands for high efficiency particulate air filter, and by definition a HEPA filter has 99.97% efficiency for particles that are larger than 0.3 microns, and the ULPA filter has a 99.997% efficiency for particles that are larger than 0.17 microns. So, the HEPA filter is a lower level of cleanliness compared to an ULPA filter. In terms of clean rooms, for example, the HEPA filter would correspond to a class 100 clean room, and the ULPA filter will correspond to a class 1 clean room. Again, if you remember our discussions from earlier, a class 100 clean room compared to a class 1 clean room is roughly 100 times dirtier, right. So, depending on the level of cleanliness you want to achieve, you will either use a HEPA filter or an ULPA filter. Obviously, there is a cost impact. The cleaner the air that you want, the more expensive it is going to be, and the certification process itself can be quite difficult. When you try to make a filter that is 99.997% effective for particles that are larger than 0.17 microns, you can imagine what kind of a challenge that will be. So, the filter rating should be something that is compatible with your process. You never want to have a filter in your process that is too much or too little. It has to be exactly what the process needs. So, that is part of this challenge. So, we have been kind of talking about filters in one range of industry applications, which is high purity manufacturing environments that require extremely contamination control conditions. At the other end, of course, there are many process industries that require filtration and purification, but not to this level. So, we will talk about some of these more common industrial filters next. Now, industrial filters are of two types: gas filters and liquid filters, right. Now, what is the challenge in industry? The challenge is the fluid stream that you are trying to filter may have highly varying concentrations of the solids. So, you can have some fluid streams that have very dilute concentrations of the solid material and some that have extremely high levels of these solid materials. So, you need to have a filtration system, or you need to have appropriate filtration systems for the fluid stream that you are trying to handle. So, that is the first thing. The second thing is, some filtration operations are required to be continuous, whereas some that are required to be discontinuous or offline type of filtration systems. So, for example, when a fluid is being fed directly into your process, you need to have a continuous filtration system which constantly keeps its purity level at a certain standard, whereas if you, for example, you are preparing water for use in your process, you may be able to do it in a batch mode and just supply it to your process on an as needed basis, in which case you can have a discontinuous filter. How you operate the filter also is a way of classifying filters. So, clearly in order for a filter to work, you have to apply a pressure difference. There has to be a delta P that pushes the fluid through the filter. There are two types of filters based on how this pressure difference is set up. One approach is to keep the downstream side at atmospheric pressure and keep the upstream side at a higher than atmospheric pressure, elevator pressure. So, this can be done by various means, pumps, blowers, centrifugal systems, which will apply pressure on the upstream side and push the fluid through the filter. The other type of filter is you keep the upstream side at atmospheric pressure and apply vacuum on the downstream side. So, you pull the fluid through the system. Now, of the two, which one do you think is more suitable for continuous operation? Vacuum filters. The reason for that is vacuum is very difficult to maintain. I mean, if you keep shutting off the vacuum and then trying to reset it, it is very hard. It takes time for the system to come back to vacuum conditions. So, anytime you use vacuum equipment in your process, you would only usually do it if it is a continuous process. You turn the vacuum on first thing when your process begins and you do not shut it off until your process stops. So, the vacuum filter has certain complexities associated with any vacuum equipment. Maintaining the vacuum is a huge challenge. Again, there are cost issues, the materials that you use, the type of seals that you provide, the necessity to prevent any kind of leak from happening. All these make vacuum based equipment in general difficult to handle, and again you only do it on a as needed basis. And so, mostly pressure filters are used, not vacuum filters, except on a as needed basis. Another way of classifying filters is based upon how much solids actually build up on the filter. So, as I said, the process fluids can have varying levels of solids, right. So, if you have a fairly high solids concentration, then pretty soon on the filter face you are going to start building up a film of material, and eventually this can get to be so thick that it introduces an additional resistance to the flow of the fluid. This type of filter is called a cake filter. You are forming a solid porous cake on top of the filter media, which adds to the pressure drop, but can also add to the filtration efficiency. Just like a fibrous filter can add filtration efficiency by adding depth, a cake filter can add to the filtration efficiency by building an additional layer on top of the filter medium. So, the three types of filters based on processing capacity are: first is a cake filter, the second is a clarifying filter, third is actually a centrifugal filter, a clarifying filter is one that handles low concentration slurries. So, this is more like what would be used in high purity applications of this kind. The amount of solids that is being processed by the filter is small enough that you never really get a big buildup of material on the face of the filter. It is essentially used for clarifying, so to speak. You have a fluid that is pretty clean to begin with trace amounts of solids, and a clarifying filter removes those solids and purifies the fluid further. A centrifugal filter, as the name suggests, is one that generates a centrifugal field and uses that to process both the cake type as well as the clarifying type of material. Clearly, this is more important for the cake type of filter because you are trying to process a large quantity of material. So, cake filter, if this is your filter medium, you start accumulating particles to a point where this essentially starts building up a layer right on top of the. So, this becomes your cake layer and this is your filter medium. Whereas in the case of a clarifying filter, you can kind of look at it almost like a depth filter where there are certain passages that are predefined and the particles just go right through. So, you do not really build up a layer on top. As the particles approach, there is sufficient space for them to penetrate into the filter and get filtered out. The third type of actually there is a fourth type which is what's called a cross flow filter. In a cross flow filter, the filter is actually held parallel to the flow of fluid. Now, virtually in every other case, as you can imagine, the fluid has to be pumped normal to the filter face in order for filtration to happen. The cross flow filter is an exception where the fluid is actually being pumped at fairly high velocities across the filter face. Now, the reason you want to do this is that this is typically again done for high concentration slurries. It prevents the problem of cake buildup, because as solids deposit on the surface, you do not allow them to build up. You use the cross flow velocity to continuously remove particles as they deposit, and so you are left with a very thin layer on the surface of the filter. There is something called an ultra pure filter which uses cross flow with extremely fine pores on the filter to achieve very high cleanliness levels of the fluid. This is typically used when you are trying to filter out things like high molecular weight vapors and colloids from a fluid stream. So, it goes down to sizes that are nano dimensional or smaller and probably represents the highest purity that we can achieve. Now, in terms of where these are used, clearly the cake filter is only used for liquid solid separations. The expectation is most gas streams will not have high enough levels of solids that you would require a cake filter. So, cake filter is normally associated with liquids, whereas the others are suitable, well, the centrifugal and the cake filter are primarily for liquid solid separations. The clarifying filter and the cross flow filter can be used both for solids as well as liquids. So, a couple of other things you should keep in mind when you are trying to design a filter system is that if you have a cake filter, eventually you are going to start building up a solid layer, it is going to introduce pressure drop and so on. So, you want to keep the cake porous during processing, and that is done by using what are known as filter aids. A filter aid is introduced to the slurry before it approaches the filter in order to increase the porosity of the cake and maintain low pressure drop and high filtration efficiency. Typical filter aids are materials like asbestos, diatomaceous silica, and few other materials. They have the property that by mixing in with the cake, they can actually make the cake more porous. Of course, eventually they have to be removed from the cake in order for them to be either discharged or reused. So, you do have to have a way of separating the filter aids from the cake before and then reusing the filter aids or preventing them from being an impurity. So, one advantage of this centrifugal filter, see, one of the problems when you are collecting a filtrate is that sometimes the filtrate may be your product and you may actually want to recover what you have filtered. You know, in many cases what you filter out you want to discharge, and that is when it is being used as a purifier. However, as we have seen before, there are cases where you want to use a filter to collect particles either for analysis or to use the particles as a product. For example, nanofilters are used to collect nanoparticles for further processing in your industry. Then you have to have a way of recovering the particles that are collected in the filter medium, which means that you have to be able to first remove the liquid that is being collected along with the particles in the cake. So, there has to be a way of removing the liquids from the filter cake before you separate out the particles, and here is where centrifugation helps, because by centrifugation you can actually spin out a lot of the excess water from the filter media, which makes it easier to separate out the particles. And of course, again in the cross flow the potential for liquid accumulation is much less, so you do not have to worry so much about the separation process. But separation of the filter liquid and separation of the filter aids are both things you have to keep in mind if you need to recover the filtered material as your product. If not, it is fine. You do have to recharge the filter once in a while, so you do have to have a way of removing whatever collects in the filter medium and discharging it. So, you do have to keep that in mind as well. Okay, so this is very basically how industry filters work, and what we need to do next is really focus on what is happening inside the filter as the filtration happens. So, let us talk about the cake filter, because that is the most common type of filter that is used in industry. So, let us say that you have a fluid that is approaching from this side and you have the filter medium here. In a cake filter, the cake starts to build up on top of the filter medium, right. So, at time equal to 0, let us say that this is your LC, which is the thickness of the cake. At time 0, this length will be equal to 0, and then with the progression of filtration time, the cake will start to build up, and then you have of course the filter medium itself. So, how do you model the resistance to flow in this case? How many components are there? There are actually 3 resistances that are in series. There is a resistance to the solids approaching the filter. At time equal to 0, they will be approaching here, and then with the progression of time they will actually be approaching the cake rather than the filter itself directly. So, there is a resistance to the flow as it approaches the filter or the cake, and there is also a, suppose this is your filter medium and the purified liquid goes out this way, there is also a resistance to this flow, but those are likely to be small, right, compared to there is a resistance across the cake as it builds up, and there is a resistance across the filter medium due to the medium itself as well as due to any particles that become impregnated in the filter medium. So, the resistance to flow can be taken as R cake plus R filter, and what does that contribute to? Pressure drop. So, delta P is again combination of delta P in the cake plus delta P in the filter. So, if you call this some PA and you call the pressure at the exit from the filter as PB, the overall pressure drop is PA minus PB. But what you can do is split it into, let us say that this is some P prime. P prime is the pressure at the interface between the cake and the filter. So, you can write this as PA minus P prime plus P prime minus PB, or delta P total equals delta P cake plus delta P filter. Now, in the last class we already talked about this. The pressure drop across a filter is some constant K, which is a function of the volume fraction times mu times an approach velocity or characteristic velocity as the fluid is pumped through, times a specific length, that is the fiber length divided per unit area. So, we know how to calculate pressure drop across the filter. How do you calculate pressure drop across the cake? You do that by modeling the cake as a porous solid, a porous bed, and there are standard equations in chemical engineering literature that express the pressure drop across a porous bed as a function of various parameters associated with the bed. There is a classic equation called the Ergun equation. Probably what we will do is later in this course, if we have time, we will go through at least one lecture where we kind of look at the basics of how we derive this, but for the time being let us take an empirical expression for this delta P. So, what we are now looking at is the delta P across the cake. It is modeled as follows: dP over dL, which is the variation of pressure across the length of the filter of the cake, can be expressed as some constant times mu times u times Sp by Vp the whole squared, which is again it is a surface area per unit volume. So, it has units of 1 over length times 1 minus epsilon squared over epsilon cubed, where epsilon is the bed porosity, it is the it is 1 minus the volume fraction of solids So, this is a general expression for how pressure varies across the length of a porous solid material like the cake. Now, if you take a small layer dl and you look at the solids volume in that layer dl, it is going to be equal to A times dl, which is a total volume of that small element, times 1 minus epsilon. Okay. Because epsilon is a porosity. What is the solid's mass in the same volume? Just multiply this by rho p. So, it is rho p times 1 minus epsilon times A times dl, and you can call this some, let us say some dm. So, that is the small amount of mass that is present in that layer dl. So, what do we do with this? So, in this expression you can write dP as equal to, you can express dl times 1 minus epsilon as dl times 1 minus epsilon is rho p or dm by rho p times A. Okay. And then you have the k times mu times u times Sp by Vp the whole squared. So, you have taken out 1 minus epsilon. So, this just becomes 1 minus epsilon by epsilon cubed. Okay. So, now you have a differential expression for dp. So, you can integrate this from Pa to p prime of dp, which is equal to delta p of the cake, and that will be the integral of this. And essentially what we are going to do is assume everything else here is constant except dm, which is varying. So, you can rewrite this as mc. So, you are just integrating dm from here to here. So, that gives you the total mass of the cake mc over rho p times a times some constant will be there, of course, times mu times u times sp by Vp squared times 1 minus epsilon by epsilon cubed. So, this is now your expression for the total pressure drop across the cake. Okay. And in fact, if you group everything here excepting mc by if you group everything here other than k mu u, whatever remains, that is mc by rho pa times sp by vp the whole squared times 1 minus epsilon by epsilon cube, you just call some parameter alpha. Okay. So, delta p cake can be simply expressed as k mu u times alpha, and as we have seen before, delta p filter can also be expressed in a very similar fashion as k mu u times a specific length. So, the total delta p is then equal to this delta p cake plus delta p filter. Okay. So, that is interesting because that gives you a very basic method of calculating pressure drop over the entire system of cake plus filter. Now, there are two modes in which filtration is done. One is called constant rate filtration, the other is called constant pressure filtration. In constant pressure filtration, you keep the pressure constant, which means that the flow rate will keep dropping over time as the solids build up in the filter. In constant rate filtration, you keep the rate of flow constant, which means you have to constantly increase the pressure. So, these are the two modes in which filters can be operated. Normally what is done is you use constant rate filtration until you reach a certain pressure, which is your maximum pressure that you can allow. After that, you keep the pressure constant and do constant pressure filtration. In other words, you allow the rate to decrease over time. So, we will see how we can actually model those two types of behavior. So far we have been kind of looking at a steady state picture, but it is important to understand the transient behavior of cake filtration systems, and we will also look at continuous versus discontinuous filtration and how we can develop some mathematical models to describe that. All right, any questions? Okay, see you in the next class.